let's talk about relative error. Now, the measurement error dx and the propagated are what we call absolute errors. So remember, when we've worked in the past with the differentials, we call dx the independent variable. So that's the error that we're going to get. Let's say we're trying to measure the length of a side. We might make some small error in measurement. Okay. The propagated error is the error of our dependent variable. So this is the error in our dependent variable. In other words, the error propagates through some quantity. So we are interested in the size of the error relative to the size of the quantity being measured or calculated. So why don't we give that quantity a letter? Let's call that quantity Q, okay? Then the absolute, if we're given an absolute error for a particular quantity Q, this is going to be delta Q, that's the amount of error, we can define the relative error as follows. That's going to be the delta Q, which is the error, divided by the total quantity, right? So this is the error divided by the total quantity. So when we divide this, this is going to give us a decimal number. All right. And one of the things we could do is we can convert, if we convert to a percentage, then this becomes something we call percentage error. So I'm going to highlight that because sometimes you'll hear people talk about what's the percentage error. And all that is just the relative error, as decimal, you're going to multiply by 100% to turn that decimal into a percentage to get the percentage error. I think this will be clear if we look at an example. So let's take a look at example 7. Let's break this down here. An astronaut using a camera measures the radius of the Earth as 4,000 miles with an error of plus or minus 80 miles. Okay, so the measurement that we have is 4,000, and this is what we call the measurement error. So maybe I'll make a little note about that. This number right here, this is the measurement error. Now I need to give that measurement error a name, and I'm going to call that measurement error dr. dr is a differential, and I call it r because we're trying to measure the radius. So I think r is a natural choice. Let's use differentials to estimate the relative and percentage error using this radius measurement to calculate the volume of the Earth. So let me highlight that word volume because this volume is this is the dependent variable. Okay, so this guy is this is the dependent, I guess, variable or quantity. So in our description up above, this would correspond to the delta Q, but we're not going to call it delta Q. We're going to use V for volume. All right. So what we're trying to do is we're really trying to calculate what dV is. So let's see how this is going to work. If they tell us that the the error in the radius is plus or minus 80 miles, then what that means is I can really say that my dr is going to be between 80 and negative 80 because it's plus or minus 80. All right. And if I'm trying to see what the propagated error is, that propagated error is going to be approximated with dV. And I know that my volume is going to be 4/3 pi r cubed. So I can calculate the differential dV by taking a derivative. So dV dr is going to be equal to, I have to use the power rule for my independent variable r. That means the 3 comes down in front, and that 3 in front is going to cancel with the 3 in the denominator. So when I take the derivative, I'm going to get 4 pi r squared. And this tells me that my dV is going to be equal to 4 pi r squared dr, like that. So I want to bound my propagated error dV. So this is going to tell me that my dV will be in between 4 pi r squared dr and 4 pi r squared dr, like that. Why do I write the same formula twice? Because I have two different values of dr. One value of dr is going to be negative 80. The other value of dr is going to be 80. And I want to bound the error dV in between those. So because I measured the radius to be 4,000, that's really telling me that my r is going to be 4,000. So let me substitute in the relevant numbers here. When I substitute in the relevant numbers, I'm going to get 4 pi, I'm going to get 4,000 squared times negative 80. That's going to be the lower bound for dV. And the upper bound for dV is going to be 4 pi times 4,000 squared times 80. Okay, now remember, I'm not looking for dV, I am looking for the relative error. So what that means is I need to divide through by whatever the actual volume is. So I wrote my volume formula up there. So let's just write that in for our denominators over here. We're going to get 4/3 pi times 4,000 cubed and 4 pi/3 times 4,000 cubed, like so. And when I simplify this down, what do I get? So we're going to pop in both of those numbers into our calculator. In fact, they're just opposite signs from each other. And when you calculate what that is, you're going to end up with negative 0.06 and 0.06. So this means our relative error is 0.06. And to convert that into a percentage, you're just going to multiply 0.06 times 100%. And then that's going to give you that the percentage error is 6%. All right. So I'm just going to highlight our final answers over here. And we will work together on some problems like this when we see each other in class. Take care, everyone.